and this is op amps. And when I think about an op amp, as we started talking about in lecture during the lab, is an op amp, and we're really talking about the micro amplifier 741 is a voltage controlled voltage source. And so typically when we draw a picture of it, we kind of imagine that we have a source, something like this here. So that means here that I'm going to have some voltage here, and we typically write it sort of like something like this here. And we say, okay, this is what the voltage source is. The language changes now. So what you're seeing here is that there's a change in language and symbol. And so what happens here is that this guy is now labeled V out, and it has a gain that's called A times the input voltage here. And so that's sort of like what it looks like here, but in reality, what does it really look like? What they do here is that the symbol changes to a diamond shape, or not a diamond, but from a diamond to a triangle. And so the symbol now looks something like this here. It looks like this. And where you see that here is that you're going to see that there's two inputs to this thing. One is a negative terminal, which is called the inverting terminal. And then there's a positive, the non-inverting. And what you find here is that you can effectively come in here and just say, well, I'm going to measure the voltage across some imaginary resistor. And the drop across this resistor is what they call the input voltage. So that would represent the Vx. It's somewhere that we have to wire that thing in here. Then the question is, where is this voltage at? Well, the dependent now looks something like this here. The dependent is now drawn here. And what you're seeing here is that you could imagine that this guy has some output resistor. Okay, that didn't go very good. So let me go back and change this here. So this guy here is called the output resistor. And then, of course, this guy here is my dependent source right in here. And so they call this V out. So that's really what this triangle does. And so what we want to do here is that we're going to use the triangle instead of the diamond that we've been using up to this point here. And so that's really what we want to talk about, is that shape of this guy and what it actually looks like. So what we want to do here is that we want to go in, and let me get organized here. And so now what I'm going to do here is that I'm going to go ahead and start dealing with that. So it goes something like this here now. So when I look at this circuit here, here's what we find. So now let's go in there and talk about the nomenclature. Nomenclature. That's probably wrong. I'm okay with it being wrong. If it really upsets you, you can look it up and spell it right. So what you're finding here is that there's an input, and typically they call the input V1. And when you look at this thing here, it comes in and you have the diamond shape like this. And then there's a terminal 2, which is called V2. And what you're finding here is that this is the positive, this is the negative. So this guy here is known as the inverting input, and this guy here is known as the non-inverting. And then there's a line, and this is a really, and I should put this other one out first here. And this is V out, the output. And what you're finding here is that there's a, you know what, I'm going to move this down. I need more space. Sorry about that. Okay, I need more space. So I'm going to take this inverting input and I'm going to move it to over here, but it's the same thing. Okay, it's the same thing. So now what happens is that what makes an op-amp operate is this line right here. This may be the most important part of the op-amp, is that there's a line that goes from here to there. And this is called the feedback line. All op-amps have a feedback line. And it's really at the core of how this looks here. So that's sort of like the nomenclature here. So when you're looking at this thing, everything is measured relative to the ground. So now what we're really saying here is that there's a ground. And we know that it's connected to the ground. So when I say V out, what I mean here is that I'm talking relative to this ground. This is the output voltage. If I look at this guy right here, this is the voltage relative to the ground. And then this guy from here would be the voltage relative to the ground. So we're always measuring these guys. And what you find here is that when you look at this, we said here that the controlling voltage is defined as Vn, which is the difference between V1, V2, and V1. Actually, I'm wrong. V2 is lower the way it's set. So I'm going to go 1 minus 2. And I know that we're just talking relative to the ground. And so what we find here is that then the voltage-controlled voltage source is defined as V out, A, Vn. So you're seeing here is that this is our linear equation that defines any dependent source. All dependent sources are linear. Now, the gain has a possible range of minus 10 to the 5 to positive 10 to the 5. So it has a gain of, it can have a gain of 100,000. Okay, and so whether you use the 100,000 doesn't really matter. But you can do it, and it happens a lot when you look at devices here. So what I want to do here is that I want to show you what it looks like. So this guy that I'm showing right here is the voltage-controlled voltage source. So this guy here is the 741 op-amp. And what you'll see here is that this guy in general has a maximum gain of 100,000. And so what you're finding here is that we really don't care about certain things here. And what we're finding here is that terminal 1 is not used. Terminal 5 is not used. And terminal 8 has no connection. Could we use 1 and 5? Yeah, but it's beyond the scope of this course here. And so what you're seeing here is that this is what you're finding here, is that you have to supply energy in order to make the op-amp work. So we're saying here is that we must supply energy to make the op-amp function. And what you're seeing here is that what you find here is that you have 2 leads, 2 inputs from the power supply. And typically what you find here is that the values that they typically set here are plus and minus 15 volts. By the way, I could also do plus or minus 10 volts. And it turns out that if you make the voltages asymmetric, the op-amp has some difficulty in operating linear throughout its range. So typically you want to make them symmetric. So what you want here is that you want symmetric voltage inputs. And you could see that these voltage inputs are occurring where? You could see that there's one right here at pin 7, which is 15, and there's another one right here, which is at pin 4, which is minus 15. So then that leaves you 3 inputs, 2 for the input of the voltage, and then 1 for the output of the voltage. And so the way we schematically draw these things is we typically draw them like this here. In all its full glory, we typically do this. So the circuit in detail looks like you have a diamond or a triangle. So you have the minus and the plus, and this is customary. And then what you have here is you have 2 voltages here. You have a voltage source coming in, and that this guy is what we typically call the positive one, and where this is the ground. So this would be terminal 7 set at plus 15 volts. And then you have a second one, which is terminal 4. And this is set typically at minus 15 volts. And so when you look at this here, you're going to find here that you now have the output, and you have everything measured relative to the ground. So once again, as we talked about before, this is V out, and then we have 2 inputs, and we call this height V1, that height V2 relative to the ground. And what we say here is that there are 2 currents that could flow. There's current I1 flowing into it, there's current I2 flowing into it, and then we can also have, in this case here, we could have a current I out that flows into it. So currents are typically flowing into the thing. But the problem is that people typically don't draw it this way. And so what we find here is that a typical sketch does not include the power supplies of plus and minus 15 volts. So what we typically do here is that we draw the op amp, and then we draw it in such a way that it looks like this only. Oops.
Is it convention to draw V2 slightly shorter?
I'm just drawing them to just show you the difference between the two relative to the ground. I mean, typically they just draw them the same length, but I think it's convenient to actually just see them without that, because you're always measuring these relative to the ground. So this guy is the common way to draw it right here. And so this is what we're going to be drawing right here. And so one of the things that I said already here is that one of the most important things about dependent sources is that they're all linear, right? So all dependent sources are linear elements. And what do I mean by this? Well, just imagine that I have a dependent source like this. And this guy, let's say, is 4. Here, I got to do something different here. I'm getting screwed up by this thing. That this guy here, what you're seeing here is that what you're finding here is that I want to make this thing 4Vx. So we all know what 4Vx means. What that really means is this is the value of the output. And so in this case, what we're really saying here is that we're saying this, that this guy right here, that guy is the input. So if I was to go graph this thing, where this is V out and this is my input Vx, well, there's a meaning to that 4. That meaning to that 4 here, that says here that the gain, which is the same as the slope, is a constant slope of 4. And that's what I mean by it being a linear element. Questions? What are the limitations of a linear dependent source? Right? What are the limitations? And it turns out that there's actually 3 of them. Okay. So the first one that we talked about yesterday in lab is called voltage saturation. And what this says here is that the maximum voltage of the op amp is plus or minus 15 volts. In other words, that the maximum output, right, the magnitude of this has to be less than V saturation, and that saturation has to be 15 volts. And that makes sense here because you can't get energy out of nothing. The only way the op amp can behave linearly is that you're putting energy into it. So what this means here is that if the dependent source has an output voltage of less than 15 volts, it behaves linear. But if the dependent source output is more than 15 volts, it reaches its maximum value. So if you were to look at this thing here, it would look something like this here. So if I have an op amp and it looks like this here, that means that as long as this guy is operating linearly, that means that it has not been saturated because it has not exceeded the 15 or minus 15 saturation point. But once it tries to exceed the 15 volt saturation, it then does this here. It just, as the saying goes, it rails off at 15 volts. So it gets saturated. So the limitation is that it has to do that. So any further increase in the input voltage, you're not going to get that. Now there's a second one here, which is called current saturation. And very similar to voltage saturation, it says that there's a maximum current that can come out of the op amp, right? So there is a maximum available current that can be drawn out of the op amp. And the way to really answer this question here is to really give you an analogy first. Now you could imagine that you have a, let's say, some type of power supply. So imagine that you have some power supply and you have some variable resistor here. So one of the things that you can do here is that you know you're going to get a current for this power supply because it's connected to this resistor right here. But the question is this here. Suppose that the resistor value is reduced to an extremely small value. In other words, in the limit as R goes to, let's say, 0, right? That's the limit of the source over the resistor here. What you're going to see here is that, of course, this approaches infinity. What real power supply is going to give you an infinite amount of current? No real power supply will ever do this. So there's a limitation of when a voltage source can give you a constant value, right? So here, there is a limitation to the linear behavior. So what you find here is that when you have an op amp, and you got to be really careful with op amps, because what people forget about is that what we're really looking at here is that we're looking at this current I out. And what you're trying to do here is that if I out becomes too large in the op amp, it stops behaving linearly. And for the 741, what we find here is that the limitations is that when I look at the output current, that this guy, which if it's less than the, so let's say here, so if it reaches the saturation current, so if it's below the saturation current, what you're going to find here is that in op amps, it's somewhere between 20 to 30 milliamps. So if it's below 20 to 30 milliamps, then the op amp behaves linearly. If you exceed the saturation current, then it behaves nonlinear. So that's the limitation right there. Different op amps behave differently. Let me make sure I did this. I did not do this because that's the whole point here. Now, there is a third one, which I don't really want to spend too much time on. By the way, I should probably say something about the oscilloscopes. I found out yesterday that the oscilloscopes actually may be at Cabrillo right now. There's only one problem. The warehouse at Cabrillo had an outbreak of COVID. And they told me that it is very, very likely that I may not be able to see them for 2 to 3 weeks. And I'm going like, holy shit, are you kidding me? I says, I'll have 2 vaccines. Let me go in there and get them. They said, no way. So we'll find out. But as it looks, I might actually cancel next week's lab. I'm not really
Send a
sure
robotic probe. You know, like the
yeah, there
Mars
you
rover.
go. I mean, hey, if they could send one to Mars, why can't we send one into the warehouse? The thing about it here is that we just have to, I'll try to get them. I sent a bunch of emails out yesterday to see if I could get to them before, this weekend, but it's falling on deaf ears, man. I can't do anything about it. But either way, I'm trying.
Yeah, call in the swarmies.
Yep. As Angel says, call the robotics club. I agree. Okay, the third one here. The third one is called the slew rate. And the slew rate, which is typically known as SR, when you look at this thing here, it tells you again, like these guys, right? Voltage saturation. At the voltage drop of the op amp is, the maximum voltage is 15. The maximum current for current saturation has to be 20 to 30 milliamps for the 741. The slew rate is a different animal. And what the slew rate does here is it says that there's a maximum of how quickly the voltage can change. Oops. With respect to time. And I don't really want to spend too much on this thing because we really have to be in front of an oscilloscope to actually show you this. So here's what really happens here. So this is really an AC thing. And I'll do this very, very, very quickly. So, and it goes like this. If one is below the slew rate, and how do you write down the slew rate? It's how quickly the voltage changes as a function of time. It's the derivative of the thing. So what you're going to find here is that you have 2 signals. So imagine So if one falls below the slew rate, here's what you find. And by the way, for the 741, it's 0.5 volts per microsecond. And so what happens here is that you have the source voltage. And what we'll say here is that we're going to make this, the black, the source voltage. So now if I do what is called a voltage follower, so this is the source voltage, which this guy I'm going to define as the input voltage. Now the output voltage, what it does here is that if I do what's called the voltage follower, then this guy is going to be right in sync. It's going to look perfect. And you won't be able to tell the difference between the input voltage versus the output voltage of the op amp. So they're going to look identical. But if you exceed, right, if one exceeds the slew rate, then what happens here is that if I was to draw this bigger, you'll find here is that the voltage can't follow anymore. Excuse me. So again, this is the input. And what you'll find here is that the output starts to look like this here. And what you're seeing here is that the output cannot follow the input. And that's because you are trying to change the voltage too fast. So, you know, in a very simplistic way, that's what we're going to do here. And we want to leave this guy right there. So let's go look at, so those are the limitations here. So now what I want to do here is I want to get into the op amp model. So the op amp model is a gnarly model, okay? And we want to use a model that's nice and simple instead of diving deep into that. And what we want to do is that we want to use what's known as the ideal op amp model.
Wait, that curve has issues.
Oh yeah, it can't follow. It exceeded the
Well,
slew rate.
No, like the V output shouldn't precede the drop in V input. It should go all the way to the edge and then go down.
I'm not really sure what you're saying.
Like V output should be high until V input drops, and then it should lag. You know what I mean? Like there's no way for V output to anticipate that V input is going to drop, which is what you're drawing there.
It actually does. When we see when we look at this on the oscilloscope, you'll see exactly this. Because as soon as it changes, it then has to drop down to 0. So what we want to do here is that we want to use a simple model of the op amp. Because the actual device is quite complicated. What do I mean by and beyond the scope of this course here? So if I was to kind of come in here, check out this. if you look at the op amp, this is what it looks like. There's a lot of crap in here. There's a
Damn.
lot of devices, and we don't want to go in and actually try to solve this thing, right? That requires a more advanced course in EE in order to do that. So instead of trying to tackle this, I recommend a simplified model. And here it goes. And the simplified model goes something like this here. What it does here is that, let me make sure, God, that mouse finding is crazy. What it does here is it does this. So this is called the ideal op amp model. And it has two simple things here. What it does here is it says that the input terminal currents are 0. In other words, I1 and I2 are 0. And the other thing here is it says that the node voltages at the inputs are equal, which is V1 equals to V2. And you're just going to have a field day with this. Because check this out. So let's draw the op amp. So this guy is going to be V2. This is V1. So what this is telling me here is that we know that the current I1 is 0 in this model. And we know that the current I2 is 0. So when I'm looking at this guy here, and right, that's what it's saying here. But then check this out. You're going to just love this. V out, which is A, right? V1 minus V2. Check this out. The second one says that V1 and V2 are the same. But if they're the same, it looks like the output looks like it's 0. Isn't this wonderful? Makes a lot of intuitive sense here. But this is a powerful, powerful model. And it works extremely well in predicting the behavior of op amps here. So we definitely want to go in and actually use this model, and you will be a master of this model. And so what you're going to find here is that there's 3 ways that you can act, 2 ways that you can solve these problems here. So, you know, maybe I should say one thing here. This is a calculational model. It's not the actual model of the op amp, it's a calculational model to get to the actual values of V1 and V2. I'm sorry, to actually get the values of V out. That's the whole goal right there, is to get the value of V out. There are 2 approaches. My favorite way, without a doubt, is that there are 2 approaches to solving op amps. One, by far, my favorite way is the simple circuits approach. And I believe is by far the strongest technique. And the second way is node analysis. You cannot use mesh analysis, and I'll explain what I mean by that later on. Okay, so it turns out that this is real simple to apply. Okay, so I would say that these are the solving strategies for op-amp circuits. Using node. And so if I talk about the first step here, what you're going to find here is that the first step, what it does here is that you need to determine the output voltage in terms of the input voltage. And this turns out to be quite tricky initially. And what you find here is that people are really going to screw up the output node. So let me ask you this question. Imagine that we have a diamond source like this. And this guy's a voltage control voltage source. And this guy's 4ix. Now, when you look at this 4ix, here's my question. When solving for node voltages, does one treat 4ix as a node? The answer is hell no. What are the nodes? The nodes are here and here, but the value of 4ix is not a node voltage. And so when you look at an op amp, what you're going to find here is, so now if you, for an op amp, when you look at this thing here, what you're going to see here is that you're going to have this output voltage here. So what you're seeing here is that I can call this guy V2 and this V1. So this is V2 and this is V1. I can write equations for V1 and V2, but I cannot write, you know what? I meant to say Vx, not Ix. Right? Sorry. Can I write a node equation for this guy here? You cannot write a node equation for Vx. So you got to remember, you got to determine the output in terms of the input voltage, but the output voltage is not a node. So then what you do here, after you write down the node equations, step 2 then is that you apply the ideal op amp model to the node equations. In other words, you said I1 and I2 equal to 0, and then you said V1 and V2 equal to the same. And then what you do here in step 3 is that then you go and you determine V out and I out for the op amp. So what I want to do here is that I want to go in and I just want to show you a couple of simple circuits. And then we want to jump into the examples here. So here's the first one that we want to look at. We want to look at what is known as the voltage follower. Okay, so let's look at some example circuits. And this is just to give you a preview of how this actually looks like. So this is one of the most famous of the op amps and super, super important to power supplies. And this is known as a voltage follower. And the voltage follower is one of the is a big reason why power supplies are actually stable. So what we want to do here is that the circuit looks something like this here. So imagine that you have some voltage source. And now what I'm going to do here is I'm going to put in a resistor. And then this is going to go into the op amp. And I'm running out of space, so I got to bring this down. Okay, so this is the positive terminal. Here's the negative terminal. And then there's a feedback resistor, a feedback wire that goes to the output. Now, even though I don't need to draw a resistor there, it's common to draw a resistor there because it actually makes people feel good by that you're measuring a voltage across a resistor instead of an open. But this is the voltage follower. So what does the op amp model really say here? Well, the first thing that it says is that it says this here. So if I look at the ideal model, what it tells us here is that the very first thing that it tells us is that both of the currents at the input terminals are 0. So let's look at that. So check this out. So this means that the current here is 0, and this means that the current here is 0. So check this out. The first thing that you should note here is look at this resistor R right above the voltage source. If there's no current in this branch, what does it do to that resistor? It kills it off. So there's no drop across that resistor. So when I go and I look at this node right here, if there's no drop across that resistor, what this tells me here is that this node tells me that V2 must be the same as the source voltage. So in this case here, we're seeing here is that I1 equal to 0 implies that there's no voltage drop across resistor R. And so then V2 must be the same as the source. But wait a minute. Then the ideal model tells us what? That V1 must be the same as V2. So when I look at this next node, you can see here that that wire tells us that this is V1 and that this node right here, this is V out. It immediately tells us then that if V2 is equal to V1 and that's equal to Vs, then because of the wire, it tells us that V out must be the same as the voltage source. And so what you're seeing here is just by looking at the ideal model, it immediately tells us that these guys that the voltage source and the output node give you exactly the same voltage. But that was a fairly simple one. One of the other most famous op amps is known as the non-inverting amplifier. Let's go look at this guy here. So this is known as the non-inverting amplifier. So here, what I'm going to do here is that I'm going to start to use notation here. And what I'm going to say here is that I have a node right there. And this guy's going to be my voltage source. Is there a voltage source connected to the ground? Absolutely. And now I'm going to do here is that I'm going to pull a fast one on you. And I'm going to switch the positive and the negative. So I know that this node here is then going to be the output node. And what you're going to see here is that I'm going to have a series of resistors connected to the ground. And typically they call this R2, this is R1. And now I'm going to have a wire that comes in and it goes to the middle here. So the circuit looks like this. Whenever you see a circuit like this, it is customary to rearrange the circuit. So what you want to do here is that you want to rearrange. So non-inverting input is below. So what I'm going to do here is that I'm going to invert this thing. And the first thing that I got to do here is that I need to draw my op amp so that the positive is down and the negative is up. Why is that? It's just customary. So look at what's connected to the positive terminal. I have that voltage source. In other words, I have a voltage source that looks like this. And this guy is connected to the ground. Now look at the output here. When you look at the output, note that there's a resistor 2, and that resistor 2 is really connected to the negative one. So here's my output right here.
You can do it, Carol. We believe in you.
Yeah.
Yeah, we believe in you. You can keep on.
This is too much pressure. I don't know. Should I not
Okay,
or let
this is
him
how
in?
we do it. We do an exam review, and you lead it, all right?
Are you the host now?
Yeah, I
she's the
am.
host.
I don't know why.
You did that to me by accident in lab yesterday, but he was still there.
Well,
Is
how's everything?
did it snow in the Santa Cruz Mountains last night?
Apparently, I don't know.
I don't think
My
so.
my
I
boss.
I don't
don't
think
just
so.
sent me-
I live up here. It was
Yeah,
pretty
not in the
cold. I
mountains
think it
that
was
I live in.
hailing.
According to SF Gate, it snowed.
Tim, aren't you up there?
Scotts Valley doesn't count as Santa Cruz Mountains.
I'm in Bonnie Doon.
Fight.
Yeah, if you're in Bonnie Doon, then it seems like if it would have snowed, you would have gotten it.
I'm not that high up though. Like I grew up here and my old house was a lot higher up and we used to get snow.
Okay.
But
He's back.
Hey, he's back.
Hey.
Carlos.
Video right away. So let's keep going.
Oh no.
Good to see you back, Carlos.
Am I back?
you've
Your
been
face
gone, huh?
isn't, but your voice is.
Yeah, but can you see my screen?
No,
No, you're not sharing anything.
Ah, damn it. Can you see my screen? God damn it. Ah,
Carlos, where are you? Are you like up in the Sierras?
Yeah, give or take.
yes. Anything?
it is still loading.
There it is.
Go.
Oh. Are you seeing my screen?
We can see the screen.
Okay, let me keep moving then. God damn it. Do that, follow the R1 resistor. So I could see that the R1 resistor come all the way to the ground. So then I'm measuring the voltage V out right here. So what I want to do here is I want to go in and I want to test this thing.
That was too much.
No,
There it went.
I didn't hear anything.
Where is he? Is he in the Sierras?
I'm pretty sure he's my neighbor. A couple of blocks.
So you have snow.
So you can see the snow, Angel.
I live in front of the freeway, and I don't see any snow.
Oh.
He has
I'm like
another
at the
house.
bottom of the valley, so.
Yeah. He has another house outside Yosemite.
There.
Oh, for real?
That makes sense.
He said he
That's what I
wasn't
was assuming until
Can
like
you guys see me at all? Can you see my screen at all?
no.
Not your screen,
No.
but you sound a lot
We
clearer.
hear you, but we can't see anything.
I mean, if you record the last 30 minutes, I'll happily watch it later.
Yeah, that's probably the best option at this point, Carlos.
Or 20 minutes.
Okay, maybe I should do that then. Record it and then upload it.
Cool.
And sorry about that. There's nothing I can do about that.
It's all
Hey,
good, Carlos.
I'll see you guys. I'll talk to you guys later. I'll post this up a little bit later.
All right. Have a good one, Carlos.
Sounds
Thank
good.
you, Carlos.
Thanks, Carlos.
Thanks,
Good luck
Carlos.
with the Wi-Fi.
Tim, your host.
Hey,
Now, this is a really special day. I've waited for this moment for many years, ever since Zoom was the thing.
Is there any way to stop this recording? Because I was going to tell you guys my